So it seems like when we look at the agreement, correct me if I'm wrong, the agreement between Cepheids and Type 1As, this again, kind of the near-ish universe around us is reasonable, but then this is not the source of the Hubble tension. The Hubble tension really comes down to comparing these Cepheids to the cosmic microwave background. Is that correct?
Well, yeah, to be clear, so when we measure supernovae, we're only measuring relative distances. And the reason for that is supernovae are rare, so we have no means of attaching an absolute scale to their distances because, for example, we can't use geometry as we do in the Milky Way to provide that absolute calibration.
Right.
So the Cepheids and the tip of the red giant branch provide an intermediate step where we can observe supernovae in the galaxies, where we can measure Cepheids and tip of the red giant branch, and then we can use geometric techniques nearby to calibrate the tip of the red giant branch and Cepheid. So there are 3 steps to this process.
It's a ladder,
so it's not
essentially,
that, yeah, it's a ladder, and it's not that supernovae agree with Cepheids. It's that Cepheids calibrate
I see.
the supernovae,
Yeah,
or
they're contingent upon
red
them.
giant.
Yeah.
They're contingent upon them,
Yeah.
and red giants calibrate the supernovae. And where the tension comes, there are 2 tensions. So one is the tension if you compare the Hubble constant that you get from Cepheids as applied to supernovae. So that's part of, Cepheids equals Cepheids plus supernovae in this discussion. Then you get 73 approximately for the Hubble constant. So we were talking about 50 and 100 before. Now the Cepheids are giving 73, and the microwave background observations, we haven't talked very much about those, but they're giving 67. So now this gap has narrowed. It's no longer a factor of 2. We're talking about the difference between 67 and 73. So
Which
that,
people at home probably think sounds pretty good. They probably think that sounds like, what's the crisis? That sounds like you're in good agreement
well, and
with
in
each
some
other.
sense it's true, right?
Yeah.
When you think of these measurements and what we're trying to do,
Yeah.
pretty difficult measurements, that kind of agreement, especially given the historical difficulty of making the measurements, it is pretty good. I think we didn't take enough time to appreciate, in a sense, how much progress had been made before making claims that, wow, this is a controversy that is indicating standard model is wrong. But so when I went to the University of Chicago, I started measuring these red giant branch stars. Our group started to undertake a calibration completely from scratch, so independent of the Cepheid distance scale. And so we thought we would either find the same answer as we were getting for the Cepheids, so the value we got from the Key project, by the way, was 72. So the Cepheids have been consistent for a couple decades now.
Okay.
And so, but you make an extraordinary claim, as Carl Sagan said, you want extraordinary evidence, and given the historical difficulty of making these measurements, you want to make sure that you've eliminated or minimized the systematics and the systematics you might not know about. So these red giant branch stars offer an opportunity to do that, to test the Cepheids. And so we thought, okay, we're either going to get 73 or 67, and we ended up getting 70. We landed right smack in the middle.
Okay, so let's take a step back. So these are the tip of the red giant branch stars, a completely independent way of measuring the expansion rate of the universe effectively. Well, really, you're getting a distance, but you convert that into the Hubble constant. Now, the Cepheids, we already spoke a little bit about this, but the problem has been with dust, as an example, that these are youngish stars. They're like the James Deans of the universe, right? They live fast, die young. And so they tend to be born in the disks of their galaxies, I would presume.
Not tend to be, yeah, that's where they form.
Right.
That's where the gas is, and that's where they're located.
So they're embedded in almost the worst possible place from an astronomy perspective. And I think with the TGRBs, the tip of the red giant branch stars, I mean, you roll that off so much more easily than I do. They have an advantage here, right? Can you tell us about that?
Yeah. So there's always a first generation of stars that form in a galaxy, right? And so disk galaxies like our Milky Way tend to have a disk, which make them a disk galaxy, and they're surrounded by an essentially spherical halo of older stars, and so the tip of the red giant branch (TRGB) stars reside also in the disk, but in the halo. As well, and so there's negligible dust in the halo.
So it's like the suburbs, the quietest part of the galaxy.
Yeah, the quietest, oldest part of the galaxy, and there's essentially no dust, and the stars are more spread out. in the disk, they're much nearer together, and so we have these overlapping blending of image problems in the disk. But the measurements of trying to see how bright is a star, it's much easier when you're not crowded by another star. And so the tip of the red giant branch method just has that advantage. We also understand them theoretically really well. We understand why they have the luminosity that they do at the tip, and these questions about whether abundance changes their luminosity. It's a very small effect, and it's easy to measure for the tip of the red giant branch stars. It's much more challenging for the Cepheids. So it's a method that has a lot of advantages, and of course, being independent, that's another big advantage.
It must have, in a way, been frustrating because people were claiming then there was this tension that the cosmic microwave background is giving a number of 67, something like this. This is from like Gaia, from WMAP, these precise cosmology experiments, and then you've got the Cepheids and the Type 1a, this ladder we spoke about, giving you 72, 73, and even though they sound similar, they are, depending how you count your errors, many sigma, we would say, apart, so statistically very significantly apart. And I guess we were hoping that your number would land on one side or the other, and we'd be like, okay, so now we know where the problem is. When you realized your answer was right in the middle, were you frustrated by that? How did you feel?
Well, the immediate reaction was sort of like shock. Really? Did it really land in the middle? It was sort of odd, and we didn't attach this absolute 0 point until the end, so we didn't know where this was going to land. So until we were, ready to apply it, and that was it. It was like one morning, here's the answer, and it was slightly a shock, I would say, but then when you think about it, given the uncertainties in any given method, it's perfectly reasonable. And so if you compare what we got for the tip of the red giant branch with the microwave background observations, they're statistically very consistent. If you compare the tip of the red giant branch with the Cepheids, they're also consistent given the uncertainties.
Because you're between them, yeah.
And so what it's telling you is, I think, something important, which is, okay, if you're going to interpret the difference between the microwave background and Cepheids as telling you something fundamental about the universe, but then you go and you make measurements, especially when you do them in the same galaxies using two different techniques, Cepheids and tip of the red giant branch, and you get a difference, well, that's telling you, you better understand what that difference is arising from, because that's not fundamental physics, right? That's either something about the stars, maybe we're learning something about astrophysics and Cepheids in general and tip of the red giant branch stars, or there are hidden systematics. And not that hidden, because it's not that big of a difference statistically.
Yeah, and I guess
not unreasonable is what I'm saying.
Right. And so is there hope of, at the moment you're in the middle, but there's a sizable uncertainty on it. I think it's a little bit larger than the Cepheid uncertainty, although it depends how you count your systematics. Is there hope of squeezing that error down and getting to a point where we should then see either a tension or a resolution?
Yeah, and that's why I'm really excited right now. So we're now in the James Webb Space Telescope realm, and our group got time in the first cycle to make observations, not just of Cepheids, not just of tip of the red giant branch stars, but both of them in the same galaxy, and an additional third method. So all three methods, same galaxies. And James Webb in the near infrared has 3 times the resolution that the infrared camera on Hubble has. And so it's like putting on eyeglasses, literally. And so when we look at the images that were observed with Hubble, and we see, very low signal measurements with lots of stars around crowding the images, and then we look at the James Webb images, and it has 10 times the sensitivity of Hubble. So these things come booming through. They're really clear. They're not crowded. And we also can look for systematic effects like differences in abundance that historically have been an issue for the Cepheids.
Right,
so I think we're going to learn an enormous amount.
So even though it's only, you're not doing hundreds of galaxies, just a few galaxies, of course it'd be great if we could do more, but if we're just given the constraints of the time, with those few galaxies, that'll essentially give you're looking at the same galaxy, so you should get the same distance, and any difference then, you can use that difference to sort of back calibrate all the previous data and figure out what's going on.
I think there's several things. One is, not only should we get the same distance, right? A galaxy has a single distance,
Yeah,
right?
yeah.
So if we find a difference, that's not fundamental physics of the early universe,
Mhm.
right? We know it's at that distance, or it should be. I'm using should again. But it's so either they're going to agree, or if the difference persists, we're going to see that, okay, this is something fundamental we don't yet understand about these kinds of stars. And that's a nice thing about having the third independent method, because that may shed some light on either increase the scatter or agree with one or the other, or maybe all three will agree when you can beat down the systematics. So we don't know where it's going to land, but either way, we're going to learn something interesting.